While we have already looked at one-sided limits, we now move into the definition of just a limit, where we consider both the left and the right limit at the same time. This defines what is just referred to as the limit, and it exists if and only if, and all that means is both sides have to be true. In other words, the limit of f of x as x approaches a from either side is equal to L if and only if, the double F is the if and only if, the limit from the left equals L and the limit from the right equals L. Let's go back to the one-sided limits that we talked about before and consider this function. Here's a graph of it. Notice that there's a hole in the graph where x equals 3. Well, if we consider the limit as x approaches 3 from the right, it is 5. If we consider the limit as x approaches 3 from the left, it is also 5. So the limit of the entire function as x approaches just 3 is 5. Do notice that f of 3 does not equal 5. It's undefined there, and that's okay. We can now define the concept of the limit by simply saying if f of x gets closer and closer to some L, as x gets closer and closer to some a, then L is the limit of f of x. So again, this is that same definition we just wrote. I've just written it again. So when does a limit exist and when does it not exist? A limit exists if and only if this L is a real number. It does not exist if the same real number is not what it equals from right and left. We say the limit does not exist, D and E, or if the limit approaches either positive or negative infinity, then the limit does not exist. Here are a few scenarios to look at. So if you notice in this picture, the left-handed limit and the right-handed limit both approach B. So the limit is B. In this case, the right-handed limit, or the right-handed limit and the left-handed limit both approach B, and f of a is B. So the limit exists. Here, f of a was not B. There was a hole in the graph. In this case, the left-handed limit approaches B, the right-hand limit approaches C. So the limit does not exist. In this one, the left-handed limit approaches negative infinity. The right-handed limit approaches B, so the limit does not exist. In this case, the left-handed limit approaches positive infinity, and the right-handed limit approaches positive infinity. So the limit does not exist, but we can at least give the direction in which the limit is unbounded. And here, the limit from the left goes to positive infinity, the limit from the right goes to negative infinity, so the limit does not exist. Let's look at just a couple examples graphically and determine the limit, and also look at some of the nuances of it. Here, the limit as x approaches 3 is going to be 1. Notice from the left, it approaches 1, and from the right, it approaches 1. However, f of 3 also equals 1. Notice if we look at the limit as x approaches, say, 0 in this case, it equals 1, but the f of 0 actually equals 2. So they don't have to be equal for the limit to exist. Secondly, we can look at this one, and let's consider the limit as x approaches -2. We'll call this one g of x. As we approach from the left, it approaches 3. As we approach 3 from the right, it also, or -2 from the right, it also approaches 3. So the limit is 3, even though the value of g of -2 is 1. Notice also that if we look at the limit of x as it approaches 2 of g of x, the limit does not exist because we are approaching different values from the left and from the right. Finally, I want to look at something called the indeterminate forms. It's important to note that in a limit problem, if the numerator has a limit other than 0, but the denominator is 0, then the function, or I'm sorry, the limit of the quotient doesn't exist. However, if both the numerator and the denominator have a limit of 0, there may be a limit of the quotient of the two. In order to determine what it may be, we have to introduce a numerical approach to this type of problem. So let's consider this here. Notice that as we approach 2, the value of the top function is going to go to 0. As we approach 2, the value of the bottom function is also going to go to 0. So we have to algebraically manipulate these two functions. We have to factor in the top, it's the difference of squares. So we can factor this into x minus 2, x plus 2. Notice that allows us to eliminate this term, resulting in 10 times x plus 2. Now, as this value approaches 2, we have 10 times 2 plus 2, which is a value of 40. Therefore, the limit here is equal to 40. As another example, consider this one. Again, we have to check that both the top and the bottom equals 0 at the value. When I plug in 5 here, I get 0. When I plug in 5 here, I get 0. So pulling out the function and working with it algebraically, we have to use our difference of cubes up top, which gives us x minus 5 times x squared plus 5x plus 25 over x minus 5 cubed. We can then divide out this and divide out one of those. And this leads us with x squared plus 5x plus 25 divided by x minus 5 squared. Now, as we look at the limit of this, we notice that the denominator still goes to 0, but the numerator no longer goes to 0. So the limit does not exist. And finally, let's consider this example. Notice that as x approaches -3, the top is going to go to 0. The bottom is also going to go to 0. When we factor, we end up with 2x minus 1 times x plus 3 over x plus 3. Again, this allows us to cancel. And then when we plug in the -3, we get a value of -7. So the limit is -7. As a rule, when you're dealing with what we're going to call the indeterminate form, we have to first make sure that both the top and the bottom equal 0 at the value that we're approaching. And then we simply factor and simplify.